My name is Harry Berman and I work for Quantinuum, a company that makes quantum computers, and in addition I also work at the University of Amsterdam in the Netherlands. And I'm a computer scientist by training, and of course as a computer scientist I'm very interested in what can you do with a quantum computer that you cannot do with a classical computer. And as it turns out, that's quite a difficult and very intriguing question. But before I delve into that, I want to start with a story of scientific discovery and an industrial advantage that comes after. And the example I want to start out with is the example of Antonie van Leeuwenhoek, a fellow Dutchman who in the 17th century, in 1674 to be precise, he constructed a microscope that was much better, 300 times better even, than what was around at the time. And by the way, he was not a scientist, he was a merchant in cloths, and he built this device for his own pleasure. And once he built it, he of course started to play with it. And one of the things that he did was he examined some drops of water from the pond behind his house in Delft, and to his bewilderment, he could see things that he didn't expect that he would see and that nobody had seen before. And what he saw were little animals that we now know are called bacteria and protozoa, but he called them animalcules, and he made a drawing that you can see here on the slide. And this was all super exciting because nobody expected there to be these animals in this clear drop of water. And moreover, this was very important because this was the birth of microbiology, which then later on led to industrial advantage, and it led to better medicine, better agriculture, food production, and biotechnology. But the point I want to make here is that this whole story first starts with one, better equipment, better hardware. Then you go into this phase of scientific discovery, and then later comes the industrial advantage phase. And often it is the case with many new technologies that it goes along these lines. And quantum computers are no different, and we are now building better quantum computers, better hardware than what was available before. So this is the new technology, the new hardware that's available. Then we are going into right now to the phase of scientific discovery, and the phase of industrial advantage will come maybe towards the end of this decennium. But we are now firmly rooted in the scientific discovery phase. And hopefully, just like van Leeuwenhoek, we will be able to see things, and in this case that means compute things, that we were not able to compute before. So now I can start my story about why and what can you do with a quantum computer that you cannot do with a classical computer. So this boils down to the question, which computational problems have a quantum speedup and which ones don't? And hopefully can convince you that this is a very difficult and deep question that has actually ties in with many deep problems in mathematics. And the reason why this is so difficult is because we don't really understand classical computation very well. It could, for example, be the case, although we don't think so, that quantum computers don't give even any additional power over classical computers. Let me explain. In computer science, and in particular in the field of complexity theory, of computational complexity theory, we try to divide the world of computational problems up into complexity classes. And one such class is the class P, which stands for polynomial time algorithms, and that means that these represent all the problems that can be solved efficiently on a classical computer. Now, there is another class that is much bigger than this class P, which is called NP. By the way, NP does not stand for not polynomial, but it stands, technical reasons, for non-deterministic polynomial time. It's not important what the exact definition of this class is, but it is important that it contains other problems that we care about in practice. For example, a very well-known problem in this class is satisfiability, and another one is the traveling salesman problem. And by the way, there is another video that you can watch online in this section of the courses that talks about the traveling salesman problem. And then we now have this new kid on the block, which stands for efficient quantum computation. It's called BQP. It's a class that you see here depicted on the slides, which looks a bit funky. It contains, of course, all the problems that can be efficiently computed on a classical computer, but it contains much more. But it doesn't contain, as far as we think, the problems of traveling salesman problem or satisfiability. And all of this is encapsulated in an even bigger complexity class called polynomial space or p-space. Again, it's not so important what the precise definitions are, just that there are these inclusion relations. And now comes the big question that we don't know how to answer, and that's the question whether this class P is equal to this class p-space. And we don't know how to prove that it's not, so it could be the case that all these classes collapse into one class, namely P, and as you can see here, then we don't have any quantum supremacy, nor do we have any quantum advantage at all. And if this is the case, then of course you don't use quantum computers at all. You just can resort to your classical computers. But luckily, the whole community, the scientific community, believes that the situation really is like this, and that all these classes are distinct. But note that from now on, I really have to use the assumption that that's the case. So whatever is being said about speed-ups of quantum computers, it really has this underlying assumption that these complexity classes do not collapse. Now, another important point that I want to make here is that all of this complexity theory traditionally is done in the worst case analysis. Now, let me explain what I mean by worst case analysis. Worst case analysis means that you look at the best algorithm for the worst instance. So you look at an algorithm that performs maybe very well on a lot of instances, but maybe it's very slow on one particular nasty instance, but on all the instances that you care about, it's fast. Nevertheless, in this traditional complexity theory, this algorithm is slow because it is slow on one instance. And somehow this is very nice for making analysis, but it is very difficult to make good algorithms in this framework. Anyhow, I hope I've convinced you that this question of which problems have a quantum speedup is a difficult and deep question. Nevertheless, we can sort of identify three types of problems, three categories of problems. The first category is the problems where we believe and where we think there is an exponential speedup of a quantum computer over a classical computer. And problems that have this property are factoring, quantum chemistry, and simulation of quantum systems. Then there is a big set of problems where there is only a polynomial speedup, like backtrack, search, and satisfiability solvers. And for example, for a polynomial speedup, you have to think here of Grover's algorithm. You may have heard of that, which has a quadratic speedup over the classical problems for searching whether an item is marked in a set of n items. You can do that in square root of n time, whereas on a classical computer you need n time. So this is an example where there is a quadratic speedup. And then there is a third class of problems where there is no speedup whatsoever. For example, for doing word processing or for doing other things like sorting or binary search. There are already very fast algorithms for this. Or for problems for which that are really, really hard, even for a quantum computer, like counting the number of satisfiable assignments of a formula. However, this middle set here of polynomial speedup is extremely interesting because many, many problems in practice fall into this category. Now, the sad news is that due to slow clock speeds of the quantum computers, to be in the near future, this quadratic or this polynomial advantage that these problems have on a quantum computer is washed away by the slowness of the quantum computers compared to the classical computers. So actually this middle class is kind of ruled out as good problems to be run on a quantum computer. However, it's ruled out because of this worst case analysis that I earlier on explained. And so it's really time and really essential to now sort of move away from this worst case analysis and go to something that is called average case or heuristic analysis. The field of heuristics, or in this case the quantum version, quantum heuristics, deals with finding algorithms that work well for the instances that you are actually interested in, and the algorithm that you devise may be very fast on the instance that you're currently examining, but it may be very slow on other instances, but that's okay because you're not interested in these other instances. But in order to devise quantum algorithms that work really well on particular instances, it seems necessary that you actually have a quantum computer available. And unfortunately, big quantum computers are not available yet, but the ones that we are currently making and the ones that will be made in the near future will actually be very useful for developing these quantum heuristic algorithms. So that's one thing. So these computers, the hardware is coming. But on the other hand, we also need a theoretical framework for this. So we need a theory to reason about these quantum heuristics. And for that, we have developed a new formalism called the Queasy instance. And a Queasy instance for a computational problem is an instance for which there is a quantum algorithm that's fast, so it's quantum easy. But on the other hand, all the classical algorithms feel queasy, meaning that they struggle with this instance and they're not fast. And so these queasy instances are very interesting because those are precisely the instances that you want to run on your quantum computer. A formal definition of these is in the making and has been made, and it uses notions of instance complexity and Kolmogorov complexity. I won't really delve into those here in this video, but I just want to share with you how it looks like and think back of this problem of satisfiability, or the traveling salesman problem. That is the set of all these instances contains probably a lot of instances that are hard both for quantum and for a classical computer, but it also contains instances that are easy even on a classical computer. Those are the easy classical instances. And then in addition, there is a set of instances that is larger for which there is a fast quantum algorithm. And those instances that are quantum easy but classically hard, those are the Queasy instances. And all the other instances are the hard instances. And so we have to focus on this purple region here in this on the slide where the instances are Queasy, because those are the instances where a quantum computer actually gives an advantage. To compare with another well-known problem, that of factoring, we know that there are some numbers that we can also factor easily on a classical computer, but we also think strongly that there are integers that we cannot factor on a classical computer. And due to the famous algorithm of Peter Shor, we know that all these instances are Queasy because there is a fast quantum algorithm for them. So this is the fundamental theoretical background framework for studying Queasy instances. Now let's see how this can be worked out in practice. So how do we work in practice with these Queasy instances? And the way we approach this is by just taking the Van Leeuwenhoek approach and just play with that microscope, play with the quantum computer. And I want to give here two examples of the things that we are currently examining. The first one is quantum topological data analysis, and the second one is on simulating physics for testing the Fermi-Hubbard model. In quantum topological data analysis, or in topological data analysis in general, we're trying to find structure, higher dimensional topological structure in data. And this is very difficult to do classically, and all the methods that we know either only focus on local parts of the data, or the topological data analysis packages, they really struggle because they just take too much time. However, we know there exist very good, and we have developed them, very good quantum algorithms that can actually be run on our near-term quantum devices. And hopefully with these in place, we will be able to see things, to compute structure that we couldn't compute before. And here you see side by side how the two algorithms, the best known classical and the best known quantum, compare to each other. And you can see that the classical ones really struggle. They feel queasy because they have to run for millennia, whereas the quantum algorithm runs in a reasonable amount of time on near-term devices. And so you can see further, can compute further than you could compute before. The other problem I want to discuss is that of superconductivity for materials at room temperature. And one of the things that people are exploring are those of cuprates. And cuprates are crystals that consist out of yttrium, barium and copper atoms, and sprinkled in this crystal are oxygen atoms. And these cuprates, they have the property of superconductivity, but we want to figure out whether they have this property at higher temperatures. And in order to do that, we have very difficult classical computations to do. And even if we want to test a small 4x4 system classically, we really don't know how to do that because the algorithms take way too much time. But again, if you try them on our near-term quantum computers, you can see that you can very soon calculate 6x6 systems, and even later on you can do 8x8 and 36x36. And so you can compute much farther than you could compute before. And once you have this in place, you can start asking other kinds of questions about the system. For example, how do more electrons affect the physics? Or what is the effect of nuclear vibrations called phonons? Or how do multiple copper oxide sheets interact? Or how does the system respond to different modes of light, for example, neutrons or voltages? And all these questions are currently out of reach, but on the next near-term computers, we can answer these questions. So, summarizing, what we have seen is that figuring out whether a quantum computer is faster than a classical computer is really a deep and difficult question. And in part it comes because we don't understand computation very well, and the other part comes from the fact that we have been analyzing these problems in a worst case fashion. Whereas I think it's very important that we start to look at these things now in a quantum heuristic way. And to do that, I have discussed with you a new notion called Queasy instances. Those are instances that are quantum easy, so there is a fast quantum algorithm, but that are classically queasy, so classical algorithms are slow, they feel queasy. And in order to, in practice, work with this notion, we have discussed two problems, that of topological data analysis and that of testing physics, and we saw that these problems inherently have these queasy instances, and we know actually how these queasy instances look like.